Determine whether each is even, odd, or neither. So in order to do that, we have to figure out what the function of negative x is. So with this first example, we need to find g of negative x. Well, that means you put negative x inside an absolute value and add 4. Well, it turns out that g of negative x, or rather the negative x inside the absolute value, is exactly the same thing as writing it as a positive x, because it doesn't matter if the sign inside the absolute value is negative or positive, you'll get the same result. So then from there you just compare the signs of this function. This is a positive term. When you put negative x in for x, it stays a positive term. This 4 is positive, it stays positive. All of the terms stayed the same, or kept the same sign. That means this function is even. For the next example over here, h of x, we need to do the same thing. We need to replace x with negative x. That means all the other x's over here will get replaced with negative x. And as long as you have negative x raised to an even power, it will equal a positive x to that even power. And that is because every pair of negative x's, or every 2 negative x's, when you multiply them together, you'll get a positive result. So even numbers are divisible by 2, so that means we can have full pairs of numbers. There won't be any stragglers left over. So negative x to an even power will equal positive x to an even power. So some examples of that would be in this function right here. Negative x to the 4th power, that is an even power, turns into x to the 4th power. Plus 2, negative x to the 2nd power, hey, guess what? 2 is an even power, so it becomes a positive x squared plus 8. Then we check the signs. This sign is positive, it stays positive. This sign is positive for the 2x squared term, it stays positive. The 8 is positive, it stays positive. All of the terms kept their signs. This function is even. So we can do something similar with these other two. So we substitute negative x in here for these 3 x's. And if you have negative x inside parentheses raised to an odd power, it becomes negative outside of parentheses x to an odd power. So what that means is that this entire thing will be negative x cubed, but it's also being multiplied by negative 1. So it'll become a positive x cubed. And with this one, positive 2 times negative x becomes negative 2x. And now when you compare these signs, a negative became a positive, and a positive 2x became a negative 2x. So all of the signs changed. That means this function is odd. And then over here with the last function, k of x, there is a mixture of changing and keeping. So I substituted negative x in for all of the x's. This one has an even power, so it becomes positive x squared. Negative and negative x is plus x plus 6. So the first sign is kept. The second sign is changed. Once you have any bit of mixture like that, some keeping and some changing, this function is neither odd nor is it even. So we just call that this is neither. For this example, you are given a transformed function, and you're asked to identify the parent function and list transformations and then graph this f of x. So how I teach this is I say we first need to find the parent function, And so the parent function would look something like this, just f of x equals the square root of x. And that is because the square root here is the defining feature of this function, right? A quadratic would have an x squared or a set of parentheses being squared. A cube root function would have a cube root, and an absolute value function would have the absolute value bars in there somewhere. But this has none of those. This has a square root. So this is a parent function. And I teach this because from this, I have my students create a table of x and f of x values. Let me see if I can move this here. There we go. And for square roots, normally with any other parent function, I just let my students go ahead and pick -2, -1, 0, and 1 and 2 for the x coordinate. But the square root is the special function, the special parent function. We can't figure out any negatives. So for the square root function, I say we pick 0, 1, and 4. No negatives because those give us I values or imaginary values, and there's no place to graph those on the real coordinate plane. So how do you figure out what the f of x values are? Well, you just substitute these x values in here for the square root, and you'll get back 0, 1, and 2. So there is the parent table along with the parent function. Let's list out the transformations. So the transformations, I'm going to underline this in pink, list out the transformations. They're here, this negative and this -2. Well, the negative, or I say the leading negative, tells me that there's a reflection over the x-axis. And the -2 tells me that there's a horizontal translation 2 units. Now, since this -2 is paired up inside the square root with x, that tells you it's going to be a horizontal translation of 2 units. But if you look at this graph, you say, oh, -2, that means you're going to go over here. No. X's do the opposite. You will be adding 2, really, or moving to the right 2 with this particular transformation. So this will be 2 units to the right. And since we're moving 2 units to the right, that means we will be adding 2 to all of the x coordinates. And so we'll get some new x coordinates over here. This will be 2, this will be 3, and this will be 6. So these are my new x's. And since the reflection over the x-axis is happening, this negative up here, this negative is not grouped up with x. So this negative is affecting the y values. So that means I'm going to come over here, and since this is -1 times the square root, I'm going to multiply all of the y values by -1. So times -1, -1, -1. So this is 0, this is -1, this is -2. These are my new y's. So now I have a new set of ordered pairs. That'll be 2, 0, right here. 3, -1, right here. And 6, -2. So 6, -2, right there. And so I know my graph will look something like this. Now, does this match up with what we know? Well, the parent function here, I'm going to graph it in black ink. The parent function starts at 0, 0, where you can see here. I'm going to use these original ordered pairs. Starts at 0, 0, 1, 1, and 4, 2. Does this blue graph look like it got reflected over the x-axis? Absolutely. Does this graph look like it was shifted to the right 2 units? Look at the starting point here and the starting point here. Absolutely. So our graph even matches up with these transformations. On this slide, we will start getting into function operations or combinations of functions. So you can see that there is a function f of x, which is the square root of x plus 3. We have a function g of x, which is x plus 2 over x minus 1. And here, h of x is just the function x minus 5. And so we're, right off the bat, being asked to find the domain of all three functions. Now, on the previous slide, I mentioned that we can't put any values in here that'll give us something negative overall. So what we do is we take the inside of the particular square root function. This only works for square roots. We take the inside of the square root, the x plus 3, and we set it to be greater than or equal to 0 and solve for x. So x is greater than or equal to negative 3. This is how you write the domain as an inequality, but interval notation is preferred. So this means x can be any number as long as it's equal to negative 3 or bigger. And that could be anything off to infinity. So the square bracket means equal to negative 3, and then the infinity to the right of that means numbers that are bigger than negative 3. So here is the interval notation of that domain. Now for the second domain, the domain of g of x, we have a different type of function. There's x plus 2 over x minus 1. Now anytime you have a variable in the denominator, you need to be wary that that denominator might be equal to 0. And we don't want it to be equal to 0, so I'm going to tell you to set the denominator to be not equal to 0, which means our x is not allowed to be 1. And you probably could see that just by looking at this, right? If this denominator is not allowed to be 0, that just means x can't be 1, because 1 minus 1 will give you 0. So let me put that not equal to there. So x cannot equal 1. So how does that look as far as a domain in interval notation is concerned? Well, I just said it can be anything. It could be negative infinity all the way over to infinity, as long as it's not 1. So this little bit here, this 1 with the parenthesis and the union and open parenthesis and another 1, that's how you take a number out of an interval. You see, you cannot equal 1, but you can get as close as you want to the left of 1. And I tell my students, hop over 1. And then you can get as close as you want to the right of 1, but you can never equal 1. And then you go off to infinity. And the third function, this one's really easy. So we already talked about a domain with the square root and a domain with a denominator here. Well, the square root, you set the inside to be bigger than or equal to 0, solve for x, interval notation. With a denominator, you take the bottom, set it to be not equal to 0, solve for x, take that number out of the domain. But this doesn't have a square root, nor does it have a denominator. So the domain here is all real numbers. Now with these last 4 down here, the domains are going to be fun, but the functions are not. And usually what ends up happening is if you add, subtract, multiply, and even for a little bit of the time when you're dividing, all of these functions will have the same domain. So let me go through the addition of these two functions, the subtraction, the multiplication, and the division. I'm just going to put all the information for all those up here at once and show you how the domains work. So here they are in all their glory. This one, the division, will take a little bit of simplification. I'll get to that in a little bit. This one does not require any simplification. The addition or the subtraction does not require simplification. Anytime you're adding, subtracting, or multiplying a square root, just leave it. Just absolutely leave it. The only thing we have to worry about here is that there is a fraction in a fraction. We'll talk about that in a second. But the point being here is if you're trying to find the domain of these functions, especially these first three, you need to find the domain of the square roots first. So we already did that. That's up here. That domain is -3 to infinity. And that's fine and dandy. But if you have a square root and a denominator, then the denominator might change this domain. Right? We found the domain of this rational expression over here. You can be anything except the number 1. Well, if you combine those two ideas together, you can be -3 or bigger, but you're not allowed to be 1. Well, that's going to change the domain a little bit. So no longer will this domain work. What I said was we can be -3 or bigger, but we cannot be 1. So here is the domain for this particular function. And wouldn't you know it, it's also the domain for this one and this one. But with this last one, this domain is not going to work. And that's because the square root is also in the denominator. Right, we have an x plus, I boogered that up. That's supposed to be an x minus 1 here. So x minus 1 is here. So again, x is not allowed to be 1 because that makes this fraction here a division by 0. Can't have that. But now also x is not allowed to be -3. With all of these other domains, we are allowing it to be -3, and you can see that in the interval notation with this square bracket. The domain for this last one is going to have an open parenthesis around the -3 because it's not allowed to be equal to -3. So the domain for this last one looks really similar, but it is fundamentally different as x cannot equal -3. So how do you simplify this thing to make it look nicer? Well, you don't want to see a fraction within a fraction. So what you do here is you multiply by the LCD of the little fractions, and this is the only little fraction we have. But you're going to multiply the top of this fraction and the bottom of this fraction, like the big fraction here. And the whole point in multiplying by an LCD is to get rid of denominators. So this simplified looks like x plus 2 over x minus 1 times the square root of x plus 3. So that's the simplification for the division here. And that sums up the entire problem. Using the functions on the previous slide, find the following combinations. So we have f plus g of 6, f minus h of 7, and hg of -1. And I just want to make sure everybody understands this operation here is multiplication. It is h times g of -1. But these all break down really nicely into the following formats. We get to evaluate f when x equals 6 and g when x equals 6, and this operation, plus, comes along for the ride. There it is, plus. And the same thing happens here. We can evaluate f at 7 and h at 7. And this operation, this minus sign, just comes along for the ride. There it is. And with this last one, I mentioned that it's h times g of -1, so we would evaluate h of -1 and g of -1, and we would multiply those results together. And so from the previous slide, f of x is the square root of x plus 3, so you just substitute 6 in for the x. 6 plus 3 is 9, the square root of 9 is 3, and we'll get to what's going on down here in a second. G of 6 is x plus 2 over x minus 1, so the 6's get substituted in for x. 6 plus 2 is 8, 6 minus 1 is 5, 8 over 5. 3 plus 8 over 5, common denominator 5. Whatever's in the denominator here needs to be multiplied by 3 to get the numerator, as that's what 3 is, 15 over 5. And then we can add the numerators together. 15 plus 8 is 23. So this can be done similarly for these other two. I will get the work up here for these in a few seconds, and then I will leave the work up for 15 seconds. Hopefully that's enough time for you to pause the video and make some sense of it. But they're both done very similarly to this one right here.